Welcome to Chemistry 112. Today is the day the test is due. So come by, turn in the test in person if you have it on paper. If you don't have it on paper, feel free to email it to me. If you're not going to see me today, that's fine. You can email it to me. Yes, hypothetically, you could drop it on Google Classroom. However you get it to me, just try to get it to me by the end of the day. And if you're going to turn it in under my door for whatever reason, make sure it's the correct door. Make sure I actually get it. So that is due today. Today we're going to talk about chemistry, about kinetics. Continue talking about that. I posted a video last Thursday going up to doing basic rate law using chemical data. This is going to be similar to the third lab we will do in a couple weeks. We still have to do the second lab, which has to do with freezing point depression. But the third lab we're going to do has to do with kinetics, where we are going to essentially do one of these rate law problems. We are going to have three values. We're going to do a series of reactions where we vary the concentration of first acetone, then acid, and then iodine, and then try to see how those three things affect the rate of the reaction. How these three things will be ordered in the reaction, meaning will this have a direct, a 1-to-1 ratio effect on the rate law? Will this have a 1-to-2 factor on the rate law, or a 1-to-0 factor on the rate law? So I ended the video last week by saying that by doing one of these problems and saying we'll start off this class by doing some more of these problems. And so I have two problems from chapter 14 homework. This is not due for, like another week or two. This Tuesday, the chapter 13 homework is kind of due. But so this chapter 14 assessment isn't due for another 2 weeks then. But we'll go ahead and go through this problem 5 and problem 6. 1.2. This first problem just looks at the rate of the effect of a one system rate law, and then it asks for determine the K. So how do we go about doing this? How do we go about determining the K on a problem like this? So always, we have to find out the base rate law. Rate equals K times the reactant raised to some order. If there's only one reactant, there's only one order. If there's two reactants, there'd be R1 and R2. Technically, the chemical formula goes in here for the reactant, but really doesn't matter. I'm writing a generalized rate law. Here's the reactant concentration. Here's the rate. So what we're doing is we're saying, okay, if the rate is 0.96 when the concentration is 0.2, and the rate is 0.48 when the concentration is 1, what effect does this concentration have on the rate? So I'm going to divide the second one by the first one. So 0.96 divided by 0.48 is 2. K over K cancels out. 0.2 to the M over 0.1 to the M is going to be the same as 2 to the M. Because this is 2 equals 2 to the M has to be 1. That's the only way that 2 equals 2. If M was any other number, that would make that statement untrue. So with that in mind, going back through, we now have rate equals K, the reactant, to the first. So we have a generalized rate law. Now we need to find out what is K. So to do that, we're going to just plug in any value. Doesn't matter which value, it should be the same K. I can take the first number, 0.48 equals K times 0.1. If I divide both sides by 0.1, I'm going to get my K, which is 4.8 equals K. Now the units of this is going to depend on the units of these. That's molarity per second, that's molarity. So if I took molarity per second and divided by molarity, molarity and molarity cancel out, leaving only 1 over seconds. But so the answer to number 5 is 4.8, 1 over seconds. So in this particular one, they ask you two things. They ask you for the number and the units. The units. Okay, might actually have to scroll down for that. They ask you for the units, so you actually have to pay attention to what you're doing. Otherwise, you're just going to be guessing the units. Not that you couldn't do that, it's just no reason to unnecessarily penalize you. The next one, and the other problem we'll do, number 6. So this one, we have a bigger rate law. We have a rate equals K, A to the M, B, A to the M, B to the N. Doesn't really matter whether A is raised to the M or N. No. We're just using these numbers as a kind of a guide. 0.37, 0.3. We're just using those as a placeholder until we figure out what the actual order is. I'm writing out just real quick the numbers so I can switch to the doc cam and not have to switch back. And then the rate. And they ask you what is the K and what is the units. Once again, in order to find the K, you must first find the rate law. You must first find the rate law. So we can't just jump straight to the end. It's a process. But no, you will not find the correct K if you do not find the correct rate law. And with that in mind, so they know in order to make you fully understand this, you have to do it right. Document camera. In order to do this, you want to choose two reactions where one of these, A or B, stays constant and the other one changes. So if I want to look at B, I'm going to compare 1 and 2. If I want to look at A, I want to look at 1 and 3. Doesn't really matter whether I find B first or A first. Order does not matter. Just to be anal attentive, I'm going to go A, then B. So I'm going to look at the rate 0.0250 over 0.0147. equals K over K 0.629 over 0.370 to the n, and 0.310 over 0.310 to the n. Those clearly cancel out and give us 1. Those clearly cancel out and give us 1. So we're looking at how does the rate change when the concentration changes. So the rate change is 1.7. The concentration change, 0.629 over 0.37. Is 1.7. So M must equal 1. Now to redo it with 2 and 1, experiment 2 and 1. So 0.0919 over 0.0147 equals K over K, thus cancel out, A over A. Even though we know this number, we know our M to be 1, we don't need to make our lives harder. Those still cancel out. And then we have our concentrations of 0.775 over 0.310. Looking at that, 0.0919 divided by 0.0147 is 6.25. We'll say 6.25. It's 6.25 something, something, something. 0.775 divided by 0.31 is 2.5 to the n. 2.5 to the n. So those do not directly equal. Now to make our lives easier, I'm going to make a reasonable guess. I'm going to guess that 2.5 is raised to the power of 2, a full integer. What happens if I square the number 2.5? I get 6.25. Because these orders are typically integers, you can make a reasonable estimate. You can make a reasonable guess. But you could use the logarithmic method to find it out as well. But we're going to make the reasonable estimate that n is equal to 2. Now I'm going to jump over here real quick because I don't want to lose my page. So right now we have the rate law. Rate equals, still finding K, but we have A to the first, B to the second, meaning the rate is directly proportional to the concentration of A, but doubly proportional to the concentration of B. So having more B greatly speeds the reaction along. Having more A speeds the reaction along. Now with this, you can use any reaction to find your K. Any of them. I'm going to use reaction 3. No particular reason, just because I felt like it. But any of these should give you the correct answer. So 0.025 molar per second equals K times 0.629 molar and 0.310 molar squared. So factoring the right side of the equation, 0.629 times 0.31 times 0.31 gives us K times 0.0604469 molar cubed. Because M times M times M is M cubed. Now solving for K, divide our m cubed value by each side. 0.250 divided by my answer. But divide by my answer. So write this down there. 0.0250 m over s. 0.06044469 m cubed. The reason I'm writing this long style is because we want to cross out one of those m's. And so your answer becomes 0.41, I'll say 414. And the units are 1 over m squared s. Because we have two m's left here and we have s left there. The units that we cancel out have to go away, and the units left behind have to remain. Do those units necessarily mean much to us mathematically? It's kind of harder for us to picture them. But those units essentially keep k valid. They keep the equation valid. So even though the units are kind of hard to comprehend, they're what we need to keep this equal to a rate. We're using that to give us a rate, molar per second. That's the whole purpose of the units of K. So because it's 1 over m squared s, so m to the negative second, s to the negative first. So that's real quick, 2 such problems that are given on the homework. 2 such problems of just this type. Okay, let's go ahead and go to the PowerPoint. Unfortunately, yeah, I didn't have more problems like that on the PowerPoint, so I had to go to the Achieve. But that is one of the reasons having that Achieve there, so we can look at those. Because where we're going from here is we're actually starting to look at differential and integrated rate laws. So that rate law we were just looking at, that whole rate law is actually the differential rate law. A differential equation looks at speeds, like at what rate does the slope change? At what rate does the slope of the slope change? So that rate was a differential. We're looking at if in differential equation, the small d stands for a delta, or the small little change in concentration, over dt, which is our change in time. Instead of putting the big triangular delta, we're using the differential delta. But it's essentially the same thing. That rate was looking at the delta A, the change in A concentration, over delta T, the change in time. And that's how we got that rate law, that K equals A to the power of M. We're looking at how that rate is related to the concentration. Now, we're going to use some calculus math, some mathemagic, if you will, to turn this differential rate law into an integrated rate law. Now, I'm not going to bother to go and expect you to do any mathematical proofs. That's not for this class. If you know the calculus, great. You could follow along. But otherwise, you don't have to. Essentially, we're getting the change of A and the A variable to one side, and the change in T and any T variables to the other side. And we're integrating both sides of the equation. So integrated rate law can factor in, essentially, if I know a concentration at one point in time, and I know what time has passed, I can calculate how much is left. Or if I know initial concentration and a final concentration, I can calculate how much time has passed. And in this way, integral will help us learn more about what is going on. This is the concept of how they do carbon dating and radioactive dating, because if a thing has a constant rate, the rate goes at a constant speed that's well known. If they measure how much we start with and how much we end with, we can calculate the time interval between them. So how old is this? Or if I know the rate of this reaction and I want it to go to 90% completion, I can calculate how long I need to make this reaction go for to achieve that. So get an idea of when to stop this reaction. So when we integrate this, we're going to put this into a standard line graph format where y equals mx plus b, where y is going to be our concentration, m is our slope, which is going to be related to our k, and x is our time, and b is our initial concentration. Now, it's going to look different depending on what rate law we have. So I'm going to do the math magic, but essentially what happens? You get, if you do this, whether, let's go ahead and go to the dot cap. Essentially, if I have a first order reaction, we're basically doing this. Real quick. I'll only show one because we only really need to show one. But integral calculus says if I have negative dA over dt equals k of a. So if I get a to this side, I would have, and t to this side, I'm going to have negative a dA equals k, 1 over a, except to divide that, k dt. Now, when I integrate this, I'm going to integrate this with respect to t. So I'm from 0 to t, and integrate this from my initial concentration, which I'm going to call A0, to my final concentration, A. Now, this one's easy, because the integral of 1 dx just becomes x. So the integral of from 0 to t of dt becomes k t. From 0, so minus 0, so that's fine. Now here's the hard one. The integral of 1 over x dx is a weird integral. We can't do that in a traditional integral fashion, so that actually becomes a natural log of x. So that becomes negative ln a minus ln a0. Now we're going to flip the sign of that negative to get it over here. And we're going to put the natural logs together to make this a little bit easier. So we get the equation ln a over a sub 0 equals negative kt. As I said, you do not have to do that. I will give you this equation every time. I never expect you to. You don't have to have calculus to do this. Okay. So essentially we get this equation, ln a sub t over a sub 0 equals a negative kt. That's the magic first order integrated rate law, or IRL, that we'll use for every first order reaction. Meaning if I have an initial concentration and a time and a k, I can find the concentration after a time period has passed, a sub t. Or if I have an initial concentration and a concentration after a certain amount of time has passed, I can find out that time. Rearranging this into the traditional format, you have the ln a sub t equals negative kt plus ln a sub 0. The ln a is our y, the negative k is our slope, the t is our x, and the plus ln a sub 0 is our b. Meaning that what the graph looks like, if I just plot concentration versus time, but if we plot ln concentration versus time, what we get is a nice linear slope, a line that you can find your k from just by observing. So that's what some people do. They will measure concentration after periods of time, and then they can plot it one of 3 different ways and see which way gives it linear, and that can be useful to help finding what order this is without going through that whole rate law situation. Now, one of the problems here is we need to find k. K will not always be given to us. So we need what's called the half-life. The half-life is a special term for this. It's a term for when half of the reaction has proceeded. The point where you get from, if you start with 10 moles, you go to 5 moles. If you start with 5 moles, you go to 2.5 moles. It's the 50% point from your starting point. So especially defining T1 half as the point where the initial concentration has been reduced by half. You can set up the equation as we see here. That ln 1/2 ln a sub 0 over a sub 0, something special happens. That 1/2 cancels out. That a sub 0 over a sub 0 cancels out. And you get natural log of 1/2. By making that negative on the other side, you can flip that around and get ln 2 equals k T1 half. Then solving for k, you get T1 half equals ln 2 over k. So the half-life of a first order reaction is based on a constant number divided by the rate constant. Meaning a half of first order reaction never changes the speed at which it proceeds halfway. It is constant for a given temperature. The only way we can change the rate on some of these guys is changing the temperature. Meaning, like, if you are going from 100% to 50%, the first one might be fast. It might be 2 days. Then 50% to 25%, the same would take another 2 days. Then from 25% to 12.5%, another 2 days. Then 12.5 to like 6 1/8, 2 days. And then 3 1/16, 2 days. It would keep going at the same time period. You would half the quantity. That first one is a big jump. The second one gets smaller and smaller and smaller and smaller until you have a point where almost nothing changes. But we'll see how we use that in a bit. Now, zero order reaction is really easy. When we do this, the zero order reaction just becomes y equals mx plus b. The concentration at time t is equal to negative kt ln a sub 0. Y equals mx plus b. Basically, you can just plot the concentration versus time, and you'll get a linear slope. Meaning, zero order reactions, it's going to keep proceeding until the concentration is 0. It's going to be at a constant rate. It's going to drop, 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 drop until we run out. Zero order is a special, very rare case. It doesn't happen too often, but when it does, it's like kind of like throws your ideas of what's going on for a loop. Now, the half-life for the zero order is a little weird. So the half-life, doing the same way, A sub 0 changes. When A sub 0 changes, the size of 1/2 A sub 0 will also change. A sub 0 doesn't cancel out. So when you have 1/2 A sub 0 minus A sub 0, what do you get? You get negative 1/2 A sub 0. So when you find the half-life of a zero-order reaction, the half-life depends on where you started at. If after 2 days, 50% went away, then after another 2 days, it's all gone because it proceeds at the same rate. The same rate. So essentially, half-life speeds up because it's just proceeding at the same constant rate. So when looking at the half-life, we actually need to know the starting point. And the second order, that's probably the weirdest one. The reaction depends on the concentration of two components reacting. So when we do our magic calculus, we get this equation. 1 over the concentration at time t minus 1 over the concentration at time 0 equals K sub t. So we don't plot the natural log. We don't plot the concentration. We plot the what's called the inverse concentration. So if the concentration is high, you're going to get a small number. If the concentration is low, you're going to get a bigger number. Rearranging this into y equals mx format, you get 1 over concentration equals kt plus 1 over concentration. One thing that changes here is this. You notice K sub t is no longer negative. With first order and zero order, kt is negative. But in this case, kt is positive. We're going to get a positive slope when we graph this. And the half order, the half-life, works very similarly. Once again, the A sub 0 does not cancel out. The A sub 0 will not cancel out, so we get an equation that looks like this. Long story short, 1 over K A sub 0 equals T1 half. If you want to follow the math is there. But generally speaking, this is your half-life equation for a second order, meaning that as concentration decreases, half-life will increase. So this reaction will greatly slow down as the reaction proceeds. So like go from 100% to 50% might take 2 days. But then to go from 50 to 25 might take 4 days or 5 days or 6 days. And then to go from 25% to 12.5%, maybe it's going to take 10 or 12 days. So it's going to keep increasing. The time it takes to decrease by half, it's going to keep increasing as the concentration decreases. Now, all this is a lot of math, so the best thing to do is just to start looking at problems. So here's 3 such problems. I'm going to jump back and forth between these guys, but typically in the problem, I will state which order. Your job is going to be partially to remember which equation is for which order, but in a take-home type situation, you can have that in front of you and how to use them. So A sub 0 over 2K T 1/2. Okay, wrote my equations down. So reading this, a zero order reaction has a half-life, so T 1/2 of 20 seconds when your concentration, your initial concentration is 0.9. Then I say, what is your concentration after 35 seconds? Go to our doc cam. How do we approach this? The first thing we need on almost all these equations is our K. We almost always need our K. We have our initial concentration. We have our 35, but we're solving a sub t. We want to know a sub t, and we want to know, we have our t is 35. We want to know what is our a sub t. But without the k, we cannot solve that. With this t1 half, we're going to say a sub 0 is 0.9 over 2 times k is 20 seconds. Solving for k, rearranging, we have 0.9 divided by 2 times 20 equals k. 0.9 divided by 40 is going to give us our k. K is 0.0225. Plugging that in there. We want what is a sub t when we have negative 0.0225 times 35 plus 0.9. So times plus 0.9. So after 35 seconds, the concentration has decreased to 0.1125. Going from 0.9 to 0.45, the half-life took 20 seconds. The second half-life would be to 0.225. So it doesn't even take, so we've essentially gone through 4 half-lives in 35 seconds. If one half-life took 20 seconds, 3 half-lives. 3 half-lives took 35 seconds. Give you a feel of how fast that proceeded. Not achieved, sorry. Pulling the next problem up. A first order reaction. So first order. First order, we have ln a sub t over a0 equals negative kt. And we have ln 2 over k equals t1 half. The half-life is 5 minutes. T1 half, 5 minutes. How long? So we want to know, what is the T? What it take to decompose to 25% of the decompose 25% of the starting material. So A sub T is 3/4 of A sub 0. We're not given A sub 0, and we're not given a straight up number for A sub T, but we can set this up in such a way that we don't need it. So back to the doc cam. First thing, as always, is find my K. So I can take ln 2 over my 5 minutes equals K. ln 2, make sure you close the parentheses, divided by 5, gives us 0.13, we'll say 86. Now I'm going to solve this. So ln, because A sub 0 is not given, but we want to get to 3/4 of A sub T remaining. 3/4. So we have ln 3/4 A sub 0 over A sub 0 cancels out, equals negative 0.1386 times T. So start with the log of 3/4 or 0.75 and divide that by my negative K. Divide that by negative 0.1386. And you get, by both sides, by 0.1386. 386. You'll get T equals 2. T equals 2. Basically, it takes 5 minutes to go through half, but it takes 2 minutes to go through a quarter. So that first quarter was 2 minutes. The second quarter is 3 minutes, meaning essentially the reaction rate is slowing down as we go. And the last one. Oh, God, I keep doing that. Last one, second order equation. Just want to show you all of them in action. Second order of equation. So I'm writing that down, the rate law, KT, and my half-life 1 over K A sub 0, T1 half. Second order reaction took 45 seconds. T equals 45 to decrease from A sub 0 of 1 to A sub T of 0.3. Just what is the rate constant, K? In this case, we don't even need the half-life at all. Don't even need the half-life at all. We can just say, set that up. So A sub T over 0.3 minus 1 over 1 equals K times 45 seconds. So 1 over 0.3 is 3.3 repeating minus 1 over 1, which is 1. So you get, so far I'm getting 2.3 repeating. 1 over m equals K times 45 seconds. So I'm going to take that number, divide 45 seconds to get my K. As I said, we're really starting to move into some real math here. Something we need to work on. If you need help, come seek it out. I can try to help us as best you can. There's only so much I can do within the classroom. But so solve that, you get a number that's 0.0519 m over 1 over ms is my K. Number that doesn't necessarily mean a lot to us right now, but if you use that later, that would be helpful to find out more stuff involving that equation. Okay. Now, real quick, another thing we could do is look at graphs of the following equations. See, in the first set, which one of these is, what order is this based on I graphed this equation 3 different ways. You may not be able to see too well, but I have tried to put a linear plot through these little circles here of the graphing it. So looking at this one, does this line fit this data points very well? No. If you look at the R squared value, the R squared tells you how well these values fit this equation. The closer this R squared value is to 1, the better this data points fit. If I look at ln of A, well, the data points fit that line perfectly. R squared is 1. And if I look at 1 over the concentration of the same data, once again, not a good fit. So this guy is clearly a first order reaction. Looking at a second set of data, if I just plot the straight up data versus time, the R squared value is very low. If I plot the natural log data, R squared is still not very good. If I plot the 1 over the concentration, The R squared becomes very good. And so this guy would be clearly a second order situation. So being able to plot these or look at these is a pretty nifty tool, save you a lot of work. So what does this all mean? What is the whole point of all these ponderous equations and complex mathematics? How can we relate numbers to the actual chemistry that's going on? And the idea is that these reaction laws are a way to probabilistically show what is the reaction happening on a molecular level. So when we discussed gases last year, when we looked at the gas law, we looked at collision models. We kind of looked very briefly at the idea of gases are bouncing around in a box. Well, we have a kind of similar thing going on in all situations. Liquids, solids, all that. These guys are colliding, and we can draw what's called the kinetic molecular theory of them to explain the gases. Well, the same kinetic molecular theory can also be used to describe this collision model of predicting how a reaction will actually work. So we're going to take the kinetic molecular theory and take it one step further. When we looked at the kinetic molecular theory, we said all molecules of gas or liquid or solid are moving at random. Obviously, there's some constraints on liquids and solids. Solids are moving within a crystal structure of some sort. Liquids are moving within whatever the container, with occasional escaping to the vapor phase. But they're sloshing around. Energy is transferred via collisions. So when one molecule bumps into another, it's transferring energy. That energy can be either speeding up things like billiard balls colliding, but they could also be breaking bonds, like two cars crashing. You're like smashing a fender, smashing like a taillight, knocking off a bumper. And of course, there's a broad distribution of energy. Not all molecules are going to have the same amount of energy at any given time, and not all molecules will keep that energy the whole time. But there is an average energy for a system, and that energy is proportional to the absolute temperature. That's what we did when we talked about gases. Well, what we're going to focus on now is that a new premise that all reactions are a result of collisions. And these collisions depend on two things. One, the molecular orientation, so how they collide. You ever see two cars collide? If you collide bumper to bumper straight on, you have certain types of damage. But if you see a straight on T-bone, you're going to see typically a lot more damage based on how they're going. So versus head on, which is going to be completely different than, say, tapping them in the back. So orientation is the same way with molecules. If I hit this from the perspective of one atom, from the perspective of another atom, depending on how they collide, it's going to change the likelihood of a bond breaking or a bond forming. But also we need energy. In chapter in the thermodynamics chapter, and the thermochemistry chapter, and also in the Lewis structure chapter, we looked at bond enthalpy. We looked at how do we make reactions go, and there has to be a certain amount of energy to start things off. We have to break a bond before we can form a bond. So when we collide, we have to collide with enough force to break the bond. If we don't, then no reaction is going to happen. Same way if I accidentally tap a car when I'm parking, I bump into it, maybe there's no damage. Sure, we collided, but it's at such low speeds, no harm, no foul. As opposed to I'm speeding down the highway, someone pulls out in front of me, and I slam into the rear. There's probably going to be a good deal of damage. So first thing we can do is draw a reaction diagram. Yes, it looks pretty shitey, but that's fine. It doesn't have to be amazing. The reaction diagram tells us kind of systematically what's going on with the progress of time. It's a generic energy versus generic time. We don't really care about the time. It's more of a reaction progress kind of thing. But the things we should be able to take from here is, one, what's the reactant? What's the product? How much energy does it take to make this go? And how much energy is formed? And we can kind of get an idea of what's formed in between. So each one will contain reactants and products. It's going to contain the activation energy, which is E sub A, energy of activation, our enthalpy, which is the energy of reaction, and one other thing, which is T double dagger, which stands for the transition state. The transition state is the peak energy state in which neither the bond has fully broken or fully formed. So I'm halfway between reactant and product. So in the case of, if I have nitrogen monoxide and ozone is degraded by nitrogen monoxide to form molecular oxygen, elemental oxygen and nitrogen dioxide. What's going to happen is that NO is going to collide with the ozone, and we're going to transfer that oxygen bond. The transition state is somewhere between the new bond forming and the old bond breaking. So we have this intermediate, this transition state up in the corner right here at the top at the high energy point where I haven't quite fully broken the bond. The oxygen hasn't fully left the ozone, but it's on its way there. It's right in the intermediate place where it could fall back to the initial starting point, or it could fall forward to the product side. And it's equally likely to go either way. Now remember what the enthalpy is. The enthalpy is the energy formed or consumed by the reaction, which is simply the difference between the reactant energy and the product energy. It does not care how high this hill is. It only cares the difference of the two low points, saying how much net energy is transferred when we make this reaction go. Is energy absorbed to make this go, or is energy released? In this case, energy is released. The net change is negative. Energy is given off. So it takes so much energy to get up the hill, but once we get up the hill, we release that energy back, and then a little bit more. That little bit more can go into the next reaction and give it a kind of a push up the hill and help push it out. And then we get even more and even more and even more. Regardless of the number of steps, this is a one-step reaction here. But regardless of the number of the steps, the enthalpy only depends on the beginning and the end energies. This is because, remember, enthalpy is one of those state functions. We don't care how it got there. We only care that it got there. We don't care how it got there. We just care the starting and ending point, which is why it only depends on the reactant and the product. It doesn't care if it goes through 3 steps in between. It only cares about the reactant and the product, because that's going to be the net change. Now, the activation energy is the difference between the reactants and the maximum energy, so the transition state. It's essentially what type of barrier is there between the reaction occurring. A high activation energy means we're going to have a slow reaction. A low activation energy means we're going to have a quick reaction. Activation energy is actually directly is going to be related to the rate constant K. Going to be related to the rate constant K, as we'll see in a minute. Recalling our bond enthalpy, it takes into account reactions are exothermic. If bonds don't break, no reaction will occur. So we need a reaction to go before we produce energy, even if it should produce energy. If we don't have the energy to break the bonds, it won't go. There is a minimum energy. Yeah, that's the activation energy. But one thing we got to remember is just like with gases in the kinetic molecular theory, the net energy is dependent on the temperature. At 0 degrees, the energy distribution is pretty low. At 20 degrees, it starts moving, and the gas molecules have to have energy above this threshold to react. At 0 degrees, very few molecules have the energy to react. So 0 degrees, the reaction is really slow. 20 degrees, maybe about 30% of the molecules have enough energy, so the reaction can happen at a 30% efficiency. At 50 degrees, it's closer to about 50%. About half the molecules have the energy they need to react. So the reaction will be a lot more efficient and it'll happen a lot faster, because 50% of all collisions will have enough energy to break the bond. So generally speaking, the higher the temperature of the reaction, the faster the molecules will be moving, the more energy they have, the more likely they're going to react. At the very first or second slide, I said that for every 10 degrees, we tend to double the reaction rate. That's because every 10 degrees, we're greatly increasing the energy of the molecules, speeding up the reaction. Now, the orientation factor is something entirely, we will typically not measure this, but we still need to consider it. Molecular orientation is essentially why they have to have the correct parts colliding. If the oxygen and ozone and the oxygen and nitrogen monoxide collide, you can see them bouncing off harmlessly. Even if they hit with enough energy, the O and the O aren't going to be attracted to each other. They're going to repel each other. So they're going to bounce off like billiard balls. But if the oxygen and the ozone collides with the nitrogen in the correct angle, the oxygen can transfer. So they need to be bouncing around and hit in just the right angle for this transfer to happen. So this is going to play a part, but we're not typically going to measure that. That's a little bit harder to measure. But of all the possible collision angles, there's a set amount which we're going to call A. That's the orientation factor. And this is true for all reactions. There's a set amount of reactions that are viable based on the orientation. Now, here's where we get an equation that's going to put these two guys together. This is the Arrhenius equation. Don't worry so much about this equation because we'll see it again on the next slide in a way that's a little bit more useful to us. The reaction rate will depend on both the orientation factor and the activation energy. The very large dependence on the activation energy. But the Swedish physicist savant Arrhenius, he's later going to work with acids and bases, but also worked with this reaction rate and activation energy. Or proposed a relationship between the two, relating temperature, activation energy, and orientation to the rate constant K. So A is our frequency factor, which is the orientation, times the inverse log, which is our E, raised to the power of negative activation energy over RT. R is our gas constant, 8.314, and T is Kelvin. So saying that if I know my activation energy and my temperature, I can find out what is my K. And K depends directly on temperature and activation energy. Now, that one is kind of bulky and annoying to use. So what we, in fact, do, we take the natural log of both sides to make this a little bit easier. The natural log of K gives us negative EA over R, which is a constant, 1 over T plus ln A. This becomes more like something we can plot. ln K being our y-axis. Negative EA over R being our slope. 1 over T being our x-axis, and ln A being our y-intercept. So if we vary temperature and measure the reaction rate, we can find out everything we need to know about the equation, including the activation energy and the orientation factor. But what's more useful is just using 2 points on the graph, not even the whole graph, just 2 points on the graph, we can find the activation energy. So activation energy determined, so we take the 2 points and we combine them together, and what we have is this. This should look familiar. This should look familiar, this equation right here. ln K1 over K2 equals EA over R, a constant, 1 over T2 minus 1 over T1. This should look very similar to what we had previously. ln P1 over P2 equals delta H over R, 1 over T2 minus 1 over T1. We used this equation last chapter, well, a chapter or two ago, looking at vapor pressure. How did vapor pressure relate to temperature? Well, we're seeing this again. How does rate constant relate to temperature? It's almost the same. The only difference is that instead of pressures, we're looking at rate constants, and instead of heat of fusion or heat of vaporization, we're looking at activation energy. But it's downright beautiful how this same equation is essentially multi-purpose. It's a really pain in the butt to do, but the fact that you see this duplication here and this completely different thing makes that much nicer in a way. But okay. So we will probably let's go ahead and do this will probably take us the rest of class. We'll do these 2 problems with this. What would be the activation energy of a reaction rate with a rate constant of 5.4 e to the negative 4th at 25 degrees C and 11.2 at 35? So let's write my equation, ln K1 over K2. Please note, you may find this in the textbook slightly flipped, depending on whether you have negative EA or positive EA. Negative EA or positive EA. So K1 is 5.4 times 10 to the negative 4th at T1, 25 degrees C. K2 is 11.2 times 10 to the negative 4th, or essentially 1.12 times 10 to the negative 3rd, T2, 35 degrees. I tried to make this a little bit easier by putting it in improper scientific notation. And of course, we want to know what is K3 at 50 degrees. Okay, so the first thing is to set up and solve for EA. One thing we have to do is turn our temperatures into Kelvin. So 25 degrees plus 273 is 298. 35 degrees plus 273 would be 308. 50 degrees plus 273 is 323. Now, ln 5.4 times 10 to the negative 4th, over 11.2 times 10 to the negative fourth. That's going to make things a little bit more convenient. Why? Because that 10 to the negative fourth and 10 to the negative fourth can cancel. Over 8.314, 1 over 308, 1 over 298. Okay. First things first, natural log of that, natural log of 5.4 over 11.2 is negative 0.7295 equals all that. We're going to EA over R. We're going to say the 1 over T. 1 over T's 308 minus 1 over 298. That's a really small number, negative 0.000108951. So we're going to take our first number. So we're going to take our first number. So I take that. 0.7295. And we're going to also multiply by our 8.314. Our activation energy becomes, EA becomes 55667 joules per mole. You may say, that is a big number. But got to remember, activation energy is typically given in kilojoules. So dividing this by 1,000 means this is going to be 55 kilojoules. And that's a reasonable number. However, I'm leaving it in joules because we need joules and joules to cancel out. So using this in the next equation means you need to leave it in joules. Now, the next equation, we want to find out what is K3. K3 will K1. K1 was 5.4 times 10 to the negative fourth. Equals 55667, 8.314. One over 323 minus 1 over 298. Wait, I did that wrong. Did I do it wrong? Yeah, I did that one wrong. Okay, let's see. That's K1 over K2. Yeah. So we would have quickly figured that out, that I did that wrong. Basically, in that when I did that wrong, I would have got a negative number instead of a positive number. And so it quickly would have, but 5567 divided by 8.314 times 1 over 298 minus 1 over 323. And that gives us 1.73904. That's equal to ln K3 over 5.4 E negative 4. So how do we solve that? Inverse log to both sides. Inverse log gives us 5.69. And we multiply both sides by 5.4. 5.4 times 10 to the negative fourth gives us essentially K3. You can either look at it as 30.7 times 10 to the negative fourth or properly as 3.07 times 10 to the negative third. Now, what I want to look at here is look at our first initial statement that we made first off, that for every 10 degrees, it approximately doubles in speed. That first time we did it, we went from 25 degrees to 35 degrees. And what happened to the speed? It went from 5.4 to 11.2. 5.4 times 2 is about 10.8. That's about double. Well, 35 to 45 would be another doubling of speed. So 10.8 times 2 is 21.6. And so now, because it's not quite and if I put I'm only putting another 5 degrees to put it to 50. But if I put it to 55, the speed would be 43. And instead it's 30. So I'm increasing by a factor of 1.5. If I increase by a factor of about 1.5, that puts it about 32 degrees, 32. So basically saying that initial statement that every 10 degrees just about doubles the reaction rate. We can see that 5 goes to about 11. 11 goes to about 20. If I doubled again, it would go to about 40. And so 30 is a very reasonable number for what we should expect here. 30 is a very reasonable number for what we should expect here. That's where we're going to leave it. We're going to say, yes, this is a lot of math. Yes, you have to work it through casually, gently, carefully. But it's a very powerful tool for learning about what's going on. To understand how this is, there's many scientists spending like their careers studying like reaction rates and understanding polymer growths, and that how can I affect this rate to make this go faster, make longer chain polymers to give certain properties. People who want to make this compound versus this compound need certain chain lengths of polymers, and they need to understand all about how this modification affects the growth rate and how this modification affects that growth rate. So if they want a polymer that's this long of chain, they like, oh, I need to put this much monomer in, and oh, I need to put this much initiator in, and that's going to affect what type of polymers they get out. But okay, so that's where we'll stop, and we'll pick up with the last little bit of this chapter on Thursday, where we essentially we'll look at reaction mechanism, how we're going to turn these rate laws into reaction mechanisms, which will be thankfully less math, but you still have to kind of reason through a good deal of this. Don't forget, send your test to me. If you don't already have it turned in to me, turn it in by the end of the day. Email it, turn it in person. I will be in lab till 3. However you want to get it to me, get it to me. Thank you. Good day.